Hello. Hi. In this lecture, we will look at Laplace transform. You will see that the Laplace transform is a generalization of the Fourier transform, which we have seen earlier. Okay. So in the Fourier transform, we have some signal x of t, which we represented in terms of complex exponentials e raised to j omega t. Right. So uh, the whole idea behind Fourier transform was that you were able to, or you are trying to represent a given x of t in terms of e raised to j omega t, which are nothing but complex exponentials with a particular frequency omega. So now and the essential idea of Fourier analysis was that any arbitrary signal can be represented as a continuum of frequencies e raised to j omega t, where omega is a continuous variable, and we get this Fourier synthesis equation, which is given here, which is there 1 by 2 pi is just a constant factor. So your x of omega e raised to j omega t d omega. Okay, so so you can think of this as a linear combination, a continuous linear combination in terms of various values of omega, and x of omega being the coefficients of that linear combination. So this is now integrated over the continuous range of omega, and by using a continuum of omegas, we are able to represent a given x of t. This was the essential idea of the Fourier transform, and Fourier analysis involved determining these x of omegas, right? And once you have those x of omegas, you can use the synthesis equation to get back to your x of t. You are representing x of t in terms of e raised to j omega t. So the main thing is that x of t we are representing in terms of e raised to j omega t. So the Laplace transform in that sense is a generalization of the Fourier transform. Instead of representing x of t in terms of e raised to j omega, we are representing x of t in terms of e raised to st, where s is in general a complex number. Okay, so s is sigma plus j omega. So you can see that in the Fourier transform, s was only j omega, right? So the difference between this one here, this is your s, whereas in the Laplace transform, s has a real part and a imaginary part. So you can see the similarity here. So e raised to st, I just expand the s here, and e raised to j omega I write as with the Euler's formula, and e of s star of t, s is a complex number, so this is e of sigma t e raised to minus j omega t. Again by Euler's formula you get this e raised to sigma t cos omega t minus j sin omega t. So if we now add this and this, and add a half term, then essentially this is e raised to sigma t cos omega t. Okay, so you can see that essentially what is happening is, if you're in place of s you had only j omega, then you would have got only cos omega t. But now since s also has a sigma plus j omega, that sigma is accommodated here, which is nothing but an exponential term is coming in front of this sinusoid. So essentially you can you can think of your e raised to st as a sinusoid multiplied by a exponential signal. So s is termed the complex frequency, okay, whereas in the j omega case, if s was only j omega, omega is usually called the angular frequency, whereas s is a more general complex frequency. Now that we started talking about e raised to st, let's see what kind of representations what kind of signals e raised to st can represent. So because we said, right, in the Laplace transform, we want to represent x of t in terms of e raised to st. Now we want to see what type of signals can e raised to st represent. So e raised to st can represent, for example, a constant sequence where the whole of s is 0. Okay, so any constant can be represented by e raised to st. You have some appropriate scaling factor to represent that particular constant, but when s is 0, e raised to st is a constant. E raised to when s is purely real, that is, if j omega is 0, s becomes only sigma, and your e raised to st becomes e raised to sigma t, where sigma is a real number. So this is nothing but a monotonic exponential function. So if your sigma is greater than 0, then this will be an increasing exponential, and if sigma is less than 0, then this will be a decaying exponential. But this is purely exponential. It will be like this or like this. Fine. Then what happens if now you put sigma as 0? Then you get your conventional complex exponential. This becomes e raised to j omega t, and that consists of real and imaginary parts, which are both sinusoids. Now you can also look at exponentially varying sinusoids, that is, when s takes the value sigma plus j omega, where sigma and j omega are both non-zero. The expansion, if you write it, it becomes e raised to xt becomes e raised to sigma plus j omega t, and if you do some simple manipulation and substitute using Euler's formula, you essentially get e raised to sigma t cos omega t plus j e raised to sigma t sin omega t. Essentially, this will now become a complex quantity, a complex time varying signal, where the real part and imaginary parts are decaying or expanding sinusoids. So they are sinusoids which are multiplied by exponentials. Now, based on the value of sigma, this sinusoid can, this exponential decaying sinusoid can either be a decaying one when your sigma is less than 0, or it will be an increasing one when sigma is greater than 0. Fine. So this thing we have seen earlier, and so e raised to st in the general case represents signals like this. So the Laplace transform which we are going to use, which we are going to describe later in this lecture, is going to represent x of t in terms of quantities like this or this, whereas the Fourier transform used quantities which were essentially only complex exponentials, which were real and imaginary parts were constant quantity sinusoids. They are periodic functions. Now there is a convenient way to represent e raised to xt, and that is by using the complex frequency plane. This is just a two-dimensional plane where the x-axis is representing the real part sigma, and the y-axis represents the j omega axis. This is the imaginary part. So you can see that increasing sinusoids like this, we have sigma greater than 0, and essentially these kind of signals live on the right hand side of the plane, and these kind of decaying signals have sigma less than 0, and they live on the left hand side of the y-axis. So this left half plane and right half plane contain different types of exponentials. So any particular value of s, e raised to st, for that one particular s will have some real part and some imaginary part, and this will be your corresponding s for some s. Okay, so all s's on this side are exponentially growing as e raised to st's, and for all the s's on this side, e raised to st is a decaying signal. Fine. I mean the real part and the imaginary part are decaying or expanding. Fine. Not much here. Let's see an example. Let's see the signal e raised to 2t cos phi t that I'm calling xt. Okay. So if I write this signal, what I'm doing is I will now just apply the Euler's formula here for cos phi t, and if I do some manipulation, I will get xt as e raised to 2 plus j5t plus 2 minus j5t. So essentially this signal has complex frequencies 2 plus j5 and 2 minus j5. So this signal consists of these two complex frequencies. So these are the two s's which make up this x of t. So essentially in this case, this is 2 plus j5 and 2 minus j5. So if I plot it on the plane, so it will be 2 plus j5, right? So it is going to be somewhere here. This is 2 and 5 and 2 minus 5. So the two frequencies will be like this. Right? This form over. So this signal will be represented in the plane by two conjugate frequencies. Fine. And of course it is on the right hand side of the plane because it is a growing sequence. Now so like we mentioned before, when s is purely imaginary, when s is only j omega, we are reduced to Fourier analysis, which we have seen earlier. Now the Laplace transform, like I said, is a generalization of the Fourier transform, where the Laplace transform of x of t is given by this expression, x minus infinity to infinity x of t e raised to minus xt dt. This gives me the expression of x of s, which is the Laplace transform of x of t. And when you, from the Laplace transform, you can come back to the time domain. This s domain is usually also known as the frequency domain. And from the frequency domain, you can come back to the time domain by applying the inverse Laplace transform, which is 1 by 2 pi j sigma c minus j infinity to c plus j infinity x of s, which is here x of s, e raised to st ds. So here we are integrating over s. So essentially what we are doing here in this expression, here we are doing complex integration. Okay. Whereas this one was over, integration was over time. So this is the thing which we already know, standard way to do this. But this one requires the inverse Laplace transform requires you to integrate over complex quantities. Bilateral Laplace transform. So in general, the Laplace transform can be used to look at signals which exist from minus infinity to less than t to plus infinity. Both signals which exist on exist less than 0 and which signals exist greater than 0. So essentially it means it can represent both causal as well as non-causal signals. On the other hand, the unilateral Laplace transform is used for causal signals. So that means we are restricting the analysis only to between between 0 and infinity. Fine. So so the difference, there is a subtle difference between the bilateral Laplace transform, which I said can represent both causal as well as non-causal signals, and the unilateral Laplace transform, which is mostly meant for analyzing causal signals. So in most cases we will be dealing with only the unilateral Laplace transform. Now there is in some cases the two Laplace transform, the only differentiating factor between the two Laplace transform is where they exist. Right. For that we come to the idea of what is known as the region of convergence. So now if you see the expression for the Laplace transform here, it is an infinite summation. Okay, we are doing it from minus infinity to plus infinity. So there is always the question of whether such a series will converge. So the set of values S for which x of s converges is known as the region of convergence of the particular Laplace transform. So let's see an example. Let's say x of t is equal to e raised to minus at ut. Okay, since we are dealing with a causal signal, this is a causal signal, we are going to look at the unilateral Laplace transform. So we have to, let's find x of s and its region of convergence. So x of s, we just apply the formula e raised to minus at ut e raised to minus st dt, infinite minus infinity to plus infinity is the range. So now, since it is a causal signal because of the u of t, our range will now reduce to from minus infinity to plus infinity, it reduces to 0 to infinity, and e raised to minus at e raised to minus st dt, and if you manipulate it a little bit, finally you will get the answer 1 minus 1 by sa e raised to minus s plus a t, where t takes the value from t takes the value infinity, and also t takes the value 0. Okay, so to find the complete value, to find the expression for x of s, we need to find out the value of e raised to minus s plus a at t equal to infinity, and subtract it from e raised to minus s plus a at t equal to 0. Now the thing is, this is a complex number. Okay, so essentially we are asked to find out the e raised to minus z t at t equal to infinity and at t equal to 0. We need to find out that value. So let's do that separately. Z is, let us assume z is equal to alpha plus j beta. Now we are going to do e raised to minus z t, which will be e raised to minus alpha t minus j beta t. See, we are always interested in the absolute value, because these are in general complex quantities. X of s in general is a complex quantity. Finally, when we are dealing with real systems and with real signals, physical systems and physical signals, we are not interested in complex numbers. We basically want the magnitude, right? So we will be always looking at the magnitude. So when we are worried about convergence and all that, we are worried about convergence of the magnitude. So if you look at the magnitude of this one, e raised to minus zt, the magnitude of this anyway is 1. So if you are worried about, if you want to find out the value of e raised to minus zt at t equal to infinity or t equal to 0, we need to worry only about e raised to minus alpha t, right? So what will this tell me? As t tends to infinity, e raised to minus zt will become 0 only if alpha is greater than 0, right? So that means, since it is, if alpha is a positive quantity, e raised to minus alpha t will tend to 0 as t goes to infinity. And similarly, e raised to minus zt will become infinity if alpha is less than 0. So essentially, this is a decaying exponential and this is a growing exponential. Correct? So applying this result to this one, we will okay, so the summary of the previous one is that at limit t tending to infinity, e raised to minus zt is 0 if the real part of z is greater than 0, and as infinity if real part of z is less than 0. So applying this to this one here, our the only difference is that now our s plus a is now, our z is now replaced by s plus a. Okay. So this means x of s will be 1 by s plus a when the real part of s plus a is greater than 0. And essentially this means that the Laplace transform of e raised to minus at ut, which was our given signal, is 1 by s plus a, provided the real part of s is greater than minus a. So only in this part, only if this condition is satisfied, will this Fourier transform converge to a finite value. Only if this condition is satisfied will this Laplace transform converge to an absolutely convert to a bounded value. So essentially, now you consider this signal, okay, e raised to minus 80 ut. This was the signal which we were looking at. So now, so this signal here we are assuming A is A is positive. Okay, so this is a decaying exponential. See, this was about S. This we are worried about. A we know is positive, and the condition for this Laplace transform to exist was that real part of S should be greater than minus A. Okay, so if you plot this Laplace transform, the region of convergence of this Laplace transform in the complex plane, the complex plane is like this. So the same complex plane which you saw earlier, the x-axis is the real part, the imaginary part is the y-axis. So the region of convergence is real part of S should be greater than minus A. So if this is the real axis, this is A is a positive number, so this is minus A, this is 0 here, so this is minus A is on the left side, and the ROC is this shaded portion, right, because it has to, S has to be greater than minus A. So whenever all the values of S which are greater than minus A is where this Laplace transform exists. It converges only in this domain. So you can evaluate this Laplace transform at S values of S here, all these places. Various values of S's you can use to evaluate the 1 by S plus A. The Laplace, this particular Laplace transform does not exist here, because if it exists here, then the values of these S values will not satisfy this condition. Real part of A in this case will be less than minus A, so the Laplace transform will not converge here. So this Laplace transform is only existing on this particular side, and that is what the ROC gives you. Now you consider the another signal, y of t is minus e raised to at u of minus t. Okay, so this signal is actually an anti-causal signal. It is u of minus t means it is an anti-causal signal. That means from infinity to 0, the signal is 0, and the signal is existing only in the from 0 up to minus infinity, or it exists it has non-zero values only for values of t which is less than 0. And so this is a exponential function. A is again positive. So this is a growing exponential, and because of the minus sign, it is a reverse growing exponential. So now if you compute the Laplace transform of this expression of this particular signal, again you will get the same expression, 1 by S plus A, which is what we got here. But the only difference is that this will have a different region of convergence. The condition for this Laplace transform to exist for this particular signal is that real part of S should be less than minus A. So again we look at the same xy plot. My minus A is here, this is my 0. So the ROC for this particular signal is this expression, but the ROC is on this side of A. Whatever values are less than A, less than minus A. So what I'm trying to tell you is here is that the expression for the Laplace transform for this, as for the expression of the Laplace transform for this signal as well as this signal is the same. It is 1 by S plus A. But the ROCs of this and this are different. The only differences in the two Laplace transforms are in the ROC. So just the expression of the Laplace transform is not enough for you to determine what is the signal. You also need to specify the ROC. Right? This is particularly true for the case of bilateral Laplace transform, because they need to represent both causal and non-causal signals, and the ROC plays an important role in determining where the signal is existing. So in case we are restricting ourselves to unilateral Laplace transform, then we will most likely not have to mention the ROC, because we know we are going to deal with only causal signals. Okay. That becomes important when we want to compute the inverse. Laplace transform. Fine. So yeah, so just get the idea clear about what is ROC and what it means. Okay, so ROC indicates where the Laplace transform exists. So now if you want to do the inverse Laplace transform, like I said, if you look at the formula here, the inverse Laplace transform requires you to do integration over S, which is a complex variable. We have to do complex calculus here. Integration is done on complex variables, which is in principle difficult. Okay, which that requires different level of mathematics. So in practice, to compute the inverse Laplace transform, we use what is known as we generally reduce it to one standard form, and we use a lookup table to determine for this expression of the Laplace transform what is the corresponding signal. Fine. So in principle we'll be using only unilateral Laplace transform, because if we restrict our analysis only to causal signals. Now for example, let us do this by example. Let's find the inverse Laplace transform for this particular signal. X of s is 7s minus 6 by s square minus s minus 6. So now this particular inverse Laplace transform, this particular Laplace transform has a particular form. So you can see that it is a ratio of two polynomials, right? So this kind of Laplace transform is known as a rational function. It is a rational function. It is a ratio of two polynomials in S. Now when you consider the numerator polynomial, if the roots of a polynomial are when the values of the polynomial for which the values of s where the polynomial takes the value 0. So if you consider the roots of the numerator polynomial, if you evaluate the x of s at the root of if you evaluate x of s at the root of the numerator polynomial, your x of s will essentially become 0, right? Because at this root, this 7s minus s will become 0, and x of s will hence become 0. Similarly, when you find out the roots of the denominator polynomial, then the denominator polynomial becomes 0, and x of s at those values of s will become infinite. So values of s for which x of s becomes 0 are called zeros of the polynomial, and for which x of s equals infinity are called poles. So zeros and poles are values of s for a particular rational function where it becomes either 0 or it becomes infinite. So pole means it just blows up because it becomes a very high value, because this value is going to be 0. So this becomes like it becomes a very large value. That is the idea of the pole. Okay, so the roots of, if you write your rational Laplace transform as P of s by Q of s, where this is P of s and this is Q of s, the roots of P of s are the zeros and the roots of Q of s are the poles. And so now coming back to this problem, to solve it, what we do, this is the given problem. So we typically use partial fractions. We represent this in terms of partial fractions. So you write it in terms of a and b, a by this one and b by this one, and you solve for a and b. So solving partial fractions is a standard technique which I think you must have learned already in engineering mathematics or some other course. So if you are not clear with it, please look up some reference. Okay, essentially it involves cancelling out one variable and equating the terms in this side, in this and in this and this, and then you solve for a and b. So essentially, by solving the partial fraction, you get a is equal to 4 and b is equal to 3, and your x of s is now 4 by s plus 2 and 3 by s plus 3. Now you need to find the inverse of this Laplace transform. So that we do it by looking at a table of Laplace transforms such as this. So it gives you the signal and its transform. Okay, so now if you want to find the inverse of this particular Laplace transform, 4 by s plus 2, see this is of the form a by 1 by s plus alpha, right? So substitute what is alpha, and the corresponding expression for the signal which has this Laplace transform is e raised to minus alpha t ut. So both of these are of that form, and then so this now becomes 4 e raised to minus 2t and plus 3 e raised to 3t ut. This we do by doing the lookup. By having this lookup table and by reducing an arbitrary Laplace transform into one of these standard forms, we can use this lookup table and compute the inverse. Okay, the u of t here is coming because we are here in this case we are looking at the unilateral Laplace transform. We are dealing with only causal signals here. Fine. So now we saw the mechanics of the Laplace transform. We saw an example of how you compute the Laplace transform, and we also saw an example of how you compute its inverse. But now we haven't still answered the question, why do we want the Laplace transform? Okay, we already have Fourier transform. Fourier transform also represents a signal in terms of complex exponentials. Okay, so why do we need the Laplace transform? That also does. That is also termed the Fourier transform is also termed the frequency analysis. Laplace transform is also frequency analysis. But why do we need? Why do we need? Does the Laplace transform give you something more than the Fourier transform? We will soon see the answer. That is the case. But let's first analyze this. Analyze this in terms of LTI systems. See, we remember what we talked about LTI systems. So there is an LTI system represented by h of t, which is the impulse response of the LTI system, and we are giving it an input xt, and you get the output yt. And the input-output relationship is given by the convolution equation. Y of t is x of t convolved with h of t, right? The h of t, I repeat, is the impulse response. Now, we also saw this earlier actually. So what happens when x of t is e raised to st? Okay, when we are giving a complex exponential as input, if this is given as a complex exponential, what will be the output? So if we have seen this earlier. So if x of t is e raised to st, the output will also be something multiplied by e raised to st. So if input is e raised to st, output is also e raised to st multiplied by a constant. And this constant is, I call it h of s, and h of s, I call it a constant because for a fixed value, for a given value of s, it is a constant. And this can be computed by h of tau e raised to minus s tau d tau. This comes from the convolution formula. Okay, essentially this is essentially the Laplace transform, but that's fine. So yeah, so why is it like this? This is because we have seen earlier that complex exponentials are eigenfunctions to LTI systems. That means whenever you give a complex exponential to an LTI system, the output is the same complex exponential with a scaling factor. Fine, that is because of the eigenfunction property. So because the system is linear and time invariant, if I have an x of t which I represent as linear combination of complex exponentials, that is a1 e raised to s1t, a2 e raised to s2t, a3 e raised to s3t. If this is my x1, it's a combination of this plus this plus this, my output will also be a combination of this plus this plus this in this manner. The coefficients AA will remain because they are the linear combination coefficients. E of s1 of t will give me h of s1, E of s1 of t. E of s2 of t will give me h of s2, E of s2 of t. And E of s3 of 3 will give me h of s3, E of s3 of t. Fine. And but now the whole idea of the Laplace transform is to get this representation. how do we represent an x in terms of these complex exponentials. That is the 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 decomposition provided to you by the Laplace transform, and you can extend this to k different inputs, right? K different complex. You can represent x of t in terms of k different complex exponentials. And not only that, practical signals like this can be represented not by a discrete combination like this, but by a continuum of frequencies, continuum of complex exponentials with where the frequency s is a continuous variable. So that is why now you consider a linear combination, a continuous linear combination where x of s is the constant factor, is x of s is the coefficient of the combination, and e raised to st is the complex exponential, and it is continuously varying over s, right? So this is the linear combination which we use to represent xt. Now this is nothing but the inverse Laplace transform. Just like you have the Fourier synthesis formulation, this is the inverse Laplace formulation where you can use these complex exponentials and write the x of t in terms of these complex exponentials. So now if you represent your x of t in terms of continuous linear combinations like this in terms of e raised to st, because it is an LTI system, the output will also be 1 by 2j x of s, this will remain unchanged, e raised to st will be h of s e raised to st ds, right? And but like I said, this is nothing but the inverse Laplace transform. So if you take the Laplace transform operator on both sides, this y of t will now become y of s, and now this will become x of s h of s, which is essentially telling you the input output relationship y of s is equal to x of s multiplied by h of s. So this is the same relationship which we saw also in the Fourier transform, that is the when you convolve in time, it is equivalent to multiplying their Fourier transforms. So it's the same property is used here, that is when the input output relation is convolution in the time domain, in the Laplace domain it is the product. So if this is your system, this is the x of s, this is the Laplace transform of x of t, this is the Laplace transform of your h of t, which is your impulse response, the Laplace transform of which is h of s, and you get y of s. The relationship between y and x is y of s is equal to y of s multiplied by h of x. I mean, y of s is equal to x of s multiplied by h of s. And generally when you write it like this, y of s is x of s h of s. This h of s, which is essentially the Laplace transform of the impulse response, is known as the transfer function, the transfer function of the system. That is, so people in control theory, people who work in control systems, etc., use this, and essentially the transfer function captures how the input is transferred to the output by the LTI system. Okay, this is in particular useful for getting the input output relationship. Now let us see the relationship to the Fourier transform. We have already seen it actually, in fact. So x of t is s of t. When x of t is e raised to st, your y of t is h of s e raised to st, which we just saw now. And we know what is the value of, we know how to get the h of s. And when, in particular, when this s is equal to j omega, your h of s evaluated at s equal to j omega will give you h of j omega, which is nothing but the Fourier transform of h of t. That is essentially your in the time domain, the system is represented by h of t, which is the impulse response. In the Laplace domain, it is represented by the transfer function, and in the Fourier domain, it is represented by h of j omega, right? There, in this particular case, this has a special name, which is nothing but the frequency response. So this is the transfer function, this is the frequency response, and this is my impulse response. So they are all essentially equivalent ways of representing the system function. So now, if I have S is sigma plus S is equal to sigma plus j omega, I want to find x of s, which is now this, which is I just substitute into the Laplace transform formula, and just by rearranging the terms, I get x of s is equal to x of t e raised to minus sigma t e raised to minus j omega t dt. Now see, this part is nothing but the Fourier transform, right? So essentially it is the Fourier transform of this, right? So essentially what this means is the Laplace transform of x of t is same as the Fourier transform of x of t multiplied by e raised to minus alpha t, where minus alpha is the real part of the frequency variable s. Okay, so this is, I think we had seen this thing earlier. So it is just like you are multiplying x of t by an exponential, and the Fourier transform of x of t multiplied by an exponential function is equivalent to the Laplace transform of x of t. So that has a practical meaning here. What it means is, now come back to this problem which we solved. Okay, so now we had seen earlier that e raised to minus at ut has this Laplace transform, and we saw that the ROC is s greater than minus a. So this is where we said the Laplace transform exists for all these values of s's. And we also said that the Fourier transform is nothing but the Laplace transform evaluated at s is equal to j omega, which is nothing but the j omega axis, right? So now see, this ROC includes the j omega axis. So for this particular signal, both Fourier transform and Laplace transform exist, because the ROC of the Laplace transform includes the location where the Fourier transform is computed. Fine, that is apparent from this also, because one sufficient condition for the Fourier transform to exist is that the signal must be absolutely summable, and that is the case here. This is a decaying exponential, and so it is absolutely summable, and hence its Fourier transform has to exist. But whereas in this case, for example, this function which we saw is a unbounded function, it keeps growing. Fine, it keeps growing, and you can see that the ROC is this side, this part, and the Fourier transform has to be computed here. So what this means is that for this particular signal, the Fourier transform does not exist, because you cannot evaluate the Laplace transform at the j omega axis, because the ROC of the Laplace transform does not include the j omega axis. So for this particular signal, you don't have a Fourier transform. The Fourier transform does not exist. So to analyze this particular kind of signal, you cannot use Fourier transform, but you can analyze this signal by using its Laplace transform. So there could be several cases where the Fourier transform of a signal or a system does not exist, but a limited amount of analysis could be done using the Laplace transform. Especially systems, things dealing with unstability, with systems which are unstable, or systems where you want to check the stability of the system, it is sometimes more beneficial to use the Laplace transform than the Fourier transform, simply for the reason that the Fourier transform may not exist. So people in control theory use this quite a lot. Okay, so that is our. We will not go more into Laplace transform. I just wanted to give you an idea of where it is used and how it is connected to the Fourier transform. And a similar thing to the Laplace transform, because Laplace transform was for the continuous variable t, right, for x of t. Now, just like we had the continuous time Fourier transform and the discrete time Fourier transform, the only difference was continuous time Fourier transform was for x of t and discrete time Fourier transform was for x of n. Similar to that, your Laplace transform is for x of t, and for x of n, when n is discrete, you have what is known as the Z transform, which is nothing but the same as the Laplace transform, but it is the independent variable of the signal is discrete. Fine. So that is the Z transform. We will not be covering it now. We will, but it is conceptually very similar. So the relationship between Laplace transform and Z transform is similar to the relationship between continuous time Fourier transform and the discrete time Fourier transform. Okay. And there are cases where the DTFT does not exist, but the Z transform will exist. Fine. So with that we will close, and we will solve some problems, etc., in the revision period. Okay. Thank you.